Hi, welcome back to Introduction to Embodied Cognitive Science. So our goal in the course is to understand what embodied cognitive science is. But to be able to get there, we need first to understand cognitive science itself so that we're able to appreciate how embodied cognitive science proposes something that's different from traditional cognitive science. So in the previous week, we saw how cognitive science emerges in the 1950s and 60s in what's often referred to as the cognitive revolution. And we also saw how the cognitive revolution uh, is actually a counter-revolution. It's a response to a prior revolution that happened in psychology in the beginning of the 20th century. And that first revolution was the behaviorist revolution, the revolution that moved away from prior understandings of psychology as a science of the mind toward thinking of psychology as a science of behavior. Um, the motivation for that shift was the realization by behaviorists that the mental states that psychologists have been talking about, are not really objectively measurable or observable. Um, we needed, in order to have access to these mental states, we need to ask a person what their experience is, right? So this method depends on introspection, and introspection is highly unreliable, right? Because I'm able to report my mental states in a certain way, you might report your mental states in a different way. So we can't really build a science around the method of introspection. That's what the behaviorists proposed. And they said, look, mental states are not objectively observable. They're not objectively measurable, so we can't build a science around mental states. What we need to build a science around is behavior, because behavior is publicly observable, right? Behavior is measurable. And so what they did was build a scientific approach that looked at environmental factors, how they act as stimuli, and how this certain stimuli lead to some behavioral responses. So their goal was then to build a science that had the goal of the prediction and control of behavior by finding the laws that relate stimuli to responses, right? The laws of conditioning that lead from some kind of stimulus to some kind of response. So this is the initial revolution. And then the cognitive revolution in the 1950s and 60s is a counter-revolution, right? So it's a response to that. Uh, Denise Cummins in her history of thinking talks about a pendulum swinging, right? So the pendulum went in one direction with with the behaviorist revolution, and then he swings back in the opposite direction with the cognitive revolution. So while behaviorists said we can't do science about mind, about mental states, the cognitivists in the cognitive revolution say that's exactly what we need to be talking about. That's exactly what we need to understand, right? So what changes with the cognitive revolution is that we go from this model where the focus of explanation in science was stimulus and response, and what happens in between stimulus and response is black boxed, right? So mental states, they're not something we talk about in science. We just look at what happens before mental events, mental states, and we look at what happens after, so stimulus and response. So the cognitive revolution changes this model and actually uh, moves the focus to the components that had been neglected by behaviorists. So we now black box, we now set aside, partially ignore what happens in the environment and the behavior itself, and we're trying to understand what happens inside, what happens internally, the internal processes that lead from um, input and output. So there's a changing language, right? We're no longer talking about stimulus and response, but we're talking about the inputs and the outputs of the system. The input is what you get through the senses, through sensations, and the output is some kind of behavioral performance. So we're trying to understand the information processing basis for transforming inputs, sensor inputs, into behavioral outputs. And this change, this shift from the behaviorist paradigm to the cognitivist paradigm was very strongly motivated by an analogy to technological developments that were happening during around the same time. which is the emergence of the modern computer, right? And there's a parallel there. There's an analogy that's often drawn between the input output system of cognition with the input output system of computers. So there's a parallel between our senses and the peripherals, the mouse, the keyboard, um, and and um, and say the behavioral output and what the computer can reveal to us through the screen or something that gets printed out, right? So, and the goal in the cognitivist paradigm is to understand the the computational processes that lead from one to the other. So that's the leading analogy or metaphor or image that motivates science under the cognitivist paradigm. It's it's this analogy between minds and computers, brains and computers. So Paul Fager talks about it being a three-way analogy because just as we understand computers as involving software and hardware, so it is with people, right? With cognitive systems, um, because in that parallel, our mind is the software and the brain is the hardware, and it's it's at this level of software and hardware that we understand cognition and we set aside the details of input and output because what we're interested in understanding scientifically is these processes that transform input into output. And it's interesting for us to note how this model, this explanatory model, um, is setting aside the body, right? So the body is where inputs come in, the body is where sensory inputs are brought into the system, and the body is also where behavior is executed. But the focus of explanation is the cognitive processes that are mediating input and output. So this is the big change that happens with the cognitive revolution, a change from the behaviorist paradigm to a paradigm that enabled talking about mental states. Um, but it's important for us to understand why. Why suddenly scientists thought it was possible to talk about mental states, right? And so if you go back to the first week, we talked about the Cartesian dualist paradigm. And so that's kind of the traditional, what I'm going to be referring to the traditional understanding of mind. And in that traditional view, um, mind happens in the private, right? Mind belongs to individuals, and only I have access to my mind, only you have access to your mind. Um, and that means that only I can study my own mind, right? Only you can study your own mind. I can tell you, I can introspect and tell you what I'm experiencing, but only I have um, privileged access to my mind. And similarly with behavior, right? Behavior is exactly the opposite in that behavior is what you can observe. And so you can see my behavior and I can see your behavior. There's no barrier to that because behaviors happen publicly. And so we can study them publicly. And that's what motivates behaviorists to focus on behavior as the objects of study in psychology. But if we think of mind differently, if we conceptualize mind in terms of computation, then that enables us to see that the mind happens privately still, right? I have my own mind, but we can study it publicly. We can, through this shift in how we conceptualize mind, we can study it, we can conduct experiments and make observations and collect data and, and, and build a science that studies mind, right? And so to understand the foundations of cognitive science, we need to understand the computational representational understanding of mind. But let's make it more exciting. We need to understand the computational representational understanding of mind.
Wow.
It's a big deal. So here's Paul Thagard giving a description of this computational representational paradigm. He says, here's the central hypothesis of cognitive science. Thinking can best be understood in terms of representational structures in the mind and computational procedures that operate on those structures. So he uses this acronym CRUM. It stands for Computational Representational Understanding of Mind. And he says the computational representation understanding of mind has been the most theoretically and experimentally successful approach to mind ever developed. Not everyone in the cognitive science disciplines agree with the computational representation understanding of mind, but inspection of the leading journals in psychology and other fields reveals that the computational representational understanding of mind is currently the dominant approach to cognitive science. So how does this approach work? He continues, he says, the computational representational understanding of mind assumes that the mind has mental representations analogous to data structures and computational procedures similar to algorithms. Schematically, in a computer program, we have data structures and algorithms that do something with the data structure. And when algorithms do something with the data structure, that's what running a program is. The parallel with mind there is that the mind is understood to comprise of mental representations and computational procedures. Computational procedures that do something with those mental representations. And that's what amounts to thinking. That's what explains behavior. Right? Behavior is mental representations going through some kind of computational procedure, some kind of computational process that yields the behavior. Steven Pinker is a famous researcher that works under this computational representational paradigm. And he says, our mental life consists of information processing or computation. Beliefs are a kind of information, thinking a kind of computation, and emotions, motives, and desires are a kind of feedback mechanism. Computation in this context refers to a generic notion of mechanical rationality. In this conception, a computational system is one in which knowledge and goals are represented as patterns in bits of matter, that is, representations. So this is a good example of a way to unpack the computational representational paradigm. Andy Clark gives a good description of the paradigm, clarifying further that it's not just an analogy when you think about it. He says, the claim is not that the brain is somehow like a computer. It's not just similar to a computer, because everything is like everything else in some respect or other. It's not just a matter of similarity. The claim is that neural tissues, synapses, cell assemblies, and all the rest are just nature's rather wet and sticky way of building a hunk of honest-to-God computing machinery. So all of these things just are components of a biological computer. Mindware, it is then claimed, is found in the brain in just the way that software is found in the computing system that is running it. So again, it's not just a comparison, it's not just a similarity, but it is an understanding that frames mind as literally a kind of computing machine, a biological machine, but a machine that performs computations. And to understand this computational representational paradigm, there are two methodological points that we need to get clear on. The first is that the computational representational paradigm involves a kind of reverse engineering. What is reverse engineering? So think of forward engineering first. So here's Steve Jobs showing a new iPhone. In forward engineering, you're designing a machine, right? And you're designing the parts of the machine, designing how the parts come together in order for the machine to perform some function. So you decide, okay, I want to build something, I want to build a device that does X, and so I'm going to design the machine. I'm going to design the device and its parts in such a way that the device can do that thing, they can perform that function, right? So you start with the goal you have for the device, and you figure out how to build something that achieves that goal for you. So that's forward engineering. Reverse engineering is when it's actually what happens with competitors in industry, right? So the competitors of Apple see the iPhone, they don't have access to the blueprint, to the plans that the designers and engineers used. All they see is a complete functioning device. And so what they have to do is, starting with that complete and functioning device, they need to try to figure out how the device was designed. They have to try to figure out how the parts work together, right, to perform that function. So um, it's kind of an investigative, detective process of guessing and trying to find out ways you could have designed something so that it would work that way, right? Trying to figure out what the parts are for and trying to figure out how they work together to make the device work. And the claim is that that's what we do in cognitive science. We're engaging in reverse engineering. We start with a complete functioning device, right? In this case, a normally functioning human being. And we need to try to figure out what the parts are for and how they work together to make the device work. That is, how the parts work together to generate the behaviors that we observe, right? Thinking and so on. And the path to that then, as we engage in reverse engineering of the mind, is we can, for example, create abstract models of information processing, and we can create computational simulations of behavior, can create robotic simulations of behavior, and these are ways of building devices that try to mimic what we see, so that they provide us a tentative explanation of what might underlie the behavior that we see in humans. So that's the first point. We're engaging in reverse engineering. The second methodological point is involves an understanding of different levels of analysis. A very influential framework for levels of analysis was put forward by David Marr in the early 80s. And Marr describes three different levels. It distinguishes between the computational level, the algorithmic level, and the implementation level. The computational level concerns why something happens, what it is for, so what the goal is. The algorithmic level asks what is being done, right? What is the process? And the implementation level asks how. How exactly is the algorithm being implemented? How is it being instantiated in some um, real device? So at the computation level, we are interested in understanding what the goal of the computation is. What is the logic of the strategy by which it can be carried out? The algorithmic level is concerned with the representation for the input and output. What is the algorithm for transforming the input into the output that's observed? And the implementation level is then asking, how can this representation and algorithm be realized physically in a real system? So the algorithmic level can be seen as a more abstract level of something that happens literally in some physical system. So the point of distinguishing between these levels is to be clear on precisely what you're trying to understand, precisely what you're trying to explain, right? So when you approach some phenomenon, Marr is suggesting that we need to be clear on whether we're trying to understand the, the, the implementation itself, right? The literal way it's realized physically, or the more abstract description of what that system is doing, right? The algorithmic transformations, or the computational level, what that process is for, what it is trying to accomplish. Marr thinks that's important for us to be clear on the computational level, but ultimately cognitive science has been in the business of um, investigating at the algorithmic level what the representations and transformation processes are that are carried out that underlie cognition and behavior. So to give an example, here's imagine a program that sorts a list of numbers. You have this list of numbers, they're random, and the goal is to starting from this list that's randomly ordered, you want to arrive at a list that's arranged from the smallest number to the largest number, right? And so at the computational level, for the program that does this, right, the computation is performed. Um, the computation that is performed is uh, to arrange the numbers such that the smallest one is first, and the next one is larger than that one, and the next one is larger than the previous one, and so on. That's why the program exists. That's what it's for, right? At the algorithmic level, that we understand the program by figuring out how that can be done. So at an abstract level of description, we come up with a way that does the sorting, how the sorting can occur so that such that the program can be implemented. And at this level, at the algorithmic level, we don't need to get into specifics of what, for example, what language to program it in, or what variable names to use, and so on. What matters is figuring out what the steps are for starting with this random list and ending with a list that we want, which is ordered. At the implementation level, then, that concerns how the program is actually written and executed on a particular computer using a particular language, right? Then you get to the specifics, and you get to flesh out and figure out how that abstract descriptions of you get to figure out how the abstract description of the steps, the computational steps at the algorithmic level are implemented physically. So what's important to see is how the computational representational paradigm proposes that we can study the mind scientifically. We can understand the mind scientifically through reverse engineering at the algorithmic level, right? So we're concerned with reverse engineering, figuring out what the parts are for and how they work together at the algorithmic level, at the abstract level of the steps that transform representations and lead from input and output. At this point, you might be wondering, but why computers? What's so special about computers that makes it possible to scientifically investigate the mind? Well, what makes computers special is the fact that they are interpreted automatic formal systems. So what does it mean to say that a computer is an interpreted automatic formal system? Let's begin with formal system. A formal system is a system that is defined by tokens, a starting state, and some rules. That is, there are objects, there are positions, and especially the starting position for the system, and then there are laws about how the positions can change, the position of the tokens. Good examples are games like checkers, tic-tac-toe, and chess. So checkers, for example, has only one type of token. There's only one type of object, right? There's a starting state of the game, and then there are rules for what can happen to those tokens. There are rules for how future states can come about. There are legal moves that you can perform with those tokens. Tic-tac-toe has two types of tokens. Um, there's a starting state of the game, and there are rules for what you can do, what can happen to those tokens. Chess, in contrast, has 6 types of tokens, and there's also a starting state, and there are laws about how future states can come about. So there are laws for how to transform the positions of each of the tokens. And what's important to understand about a formal system is that, first of all, it's perfectly definite. So there's no room for judgment calls. There's no room for interpretation or subjective preference. The system is defined by the tokens, the positions, and the rules for transforming the position of tokens. And so there's an objective account to be given for given move. If you move a piece in the game, there's a definite answer as to whether that movement is legal or not, whether that move is following the rules or not. Formal systems are also finite. That means that they are finitely playable and checkable. So within a, a finite amount of time, you can determine if a move is legal or not. Formal systems are also self-contained. That means that only tokens, positions, and the legal moves matter. There may be other factors, but for the formal system itself, these factors are irrelevant because the system is defined in terms of simply these components. Um, and importantly, a formal system is medium independent. That means that it can be implemented in one way, but it could also be implemented in other ways. And it's still the same system, formally speaking, right? So the tokens can be different. You can change some characteristics of the tokens, um, but the the rules for transforming those tokens, whatever they are going to be the same. So for an example, consider the game of football, which right involves these bits of wood or plastic and a table of certain dimensions. But the same game can be played in a completely different implementation, right? So the formal system is the same. It doesn't depend on the medium, the specific medium that it is implemented in. Similarly, going back to the game of chess, the pieces that you use can be made of wood or plastic or glass or metal. Um, but what matters is how you're using those pieces, those tokens, right? So the rules that are you using for moving the pieces around on the board. So that means that you could play chess with helicopters. Why not, right? So if there was the right number of buildings or places where you can land your helicopters, you have the right number of helicopters, right? And you follow the rules for transforming the positions of these helicopters, you're playing chess, right? Even though you're not using little pieces of wood or plastic or metal, or right? So the game of chess is a formal system, and here you see how it's medium independent. So a formal system is a system that's fully defined by the tokens, the, the starting state and the positions that are possible, and the rules, the laws that make transformations of positions um, acceptable. So that's what a formal system is. A formal system is automatic when it can carry out all by itself token manipulation according to the rules. So if the system can play itself, it's an automatic formal system, right? A chessboard with little pieces of plastic or wooden tokens, right? Or the helicopter chess is not automatic, right? It requires humans. It requires people to play the game. Now, a formal system that's automatic will also be interpreted when, besides the syntax, besides the rules that dictate how the tokens are um, transformed, how they're moved around, um, when besides the syntax, the system is also sensitive to semantics. So what does that mean? What is the difference between syntax and semantics? So we have here an example of a weird sentence. Colorless green ideas sleep furiously. So syntax refers to the grammatical function of these terms. So they're colorless is an adjective, green is an adjective, ideas is a noun, sleep is a verb, furiously is an adverb. So at the syntactic level, we can analyze the sentence by identifying the function of the parts. At the semantic level is where we consider the meaning of the terms, how these terms refer to something in the real world. And so even though And so at the semantic level, we can see that the sentence is meaningless, right? It's a crazy sentence. But at the level of syntax, there's nothing particularly wrong about it because it is putting the tokens in an order that is allowed by the rules, right? The rules of grammar dictate how different objects, words can be put together to form a sentence that's considered grammatical. And this one is grammatical. The issue with it is at the level of semantics, the level of meanings. For another example, consider the sentence, I saw the bank, right? If you look at this picture and you say, I saw the bank, right? You, you could be talking about the bank, the financial institution that's there. You could also be talking about the edge of land where land meets the water in a river, because that's also called a bank, right? So notice how the the two sentences, if you say when you say I saw the bank and you mean the financial institution, or if you say I saw the bank and you mean the land formation, these are syntactically identical, right? The tokens that make up the sentence are syntactically identical. They perform the same grammatical function. The difference between the two sentences is a difference of semantics, a difference of meaning. Okay, so that's the distinction between syntax and semantics. So going back then, when we say the computers are interpreted automatic formal systems, we're saying that computers are automatic formal systems that, besides following syntax, because all formal systems follow syntax, that's what the rules for transforming tokens mean. So besides following syntax, computers are interpreted in that they are sensitive to semantics in some way that we'll see. This is John Hoglan. It says, so formal tokens can lead two lives: syntactical, formal lives, in which they are meaningless markers, moved according to the rules of some self-contained game. And if the system is interpreted, then the tokens can lead semantic lives, in which they have meanings and significant relations to the outside world. So again, in a sentence, the tokens, the words, bear some relation to the world, right? But the relation that the terms bear to the world are different from the fact that the tokens can be put together, can be combined following syntactical rules, following grammatical rules. And we saw that one example of a sentence that is following the rules of syntax, but the semantics is messed up. So a formal system that is automatic is specified purely in terms of syntax. Because meanings are not physical, computers cannot be defined in terms of or interact with meaning. Computational processes must ignore semantics, right? So the processes of transforming the tokens doesn't involve or interact with the meaning of those tokens. But because computers are interpreted automatic formal systems, that means that the tokens have meanings and that the rules respect those meanings. The game of chess is following rules, so there's a syntax for the game, but the tokens themselves don't have a meaning. They don't bear some relation to some other thing, right? And that's not relevant for the game, for playing the game of chess. But in an interpreted automatic formal system, tokens have meanings. And so besides following rules, besides simply following rules, um, the system is implementing rules that respect the meaning of those terms. That means that the rules are truth preserving. That means that if you start with true sentences and you apply the rules, then you're going to end up with other true sentences, right? If rules were not truth preserving, that would mean that if you start with true sentences and you apply the rules, you could end up with false sentences, and that's not the case, right? The rules in an interpreted automatic formal system are sensitive to semantics, even though the system itself might be oblivious to the meaning that the tokens bear to things in the real world. So again, John Hugland explains this for us. He says the notions of medium independence and formal equivalence are crucially important to artificial intelligence and to computational psychology in general. Though some of the significance can only emerge as our discussion proceeds, the basic point can be stated crudely. Brain cells and electronic circuits are manifestly different media. But maybe at some appropriate level of abstraction, they can be media for equivalent formal systems. In that case, a computer mind might be as much a real, genuine mind as helicopter or computer chess is genuine chess, only in a different medium, right? So the parallel there is between chess being played with regular pieces or with helicopters, say, um, and the two being different implementations of the same formal system, implementations in different media, and then mind involving some kind of medium that's different from the medium used by computers, but the same formal system is being implemented in both. So going back to the schema that Thagard proposed, in a computer program, we have data structures and algorithms that transform those data structures, and that's what running a program is. And in mind, we have mental representations and computational procedures that transform those mental representations, and that's what thinking is. So there's a parallel between the two. In the program, data structures, and in mind, mental representation. Those are the tokens of the formal system. There are also rules. In a computer program, the rules are algorithms. In the mind, they're computational procedures. And when you combine the tokens and the rules of this formal system, when they work together, that's what running a program is in the context of computers, and that's what thinking is in the context of human behavior. And this is relevant because this is what enables us to understand mind scientifically, even though it's a private matter. This is what makes mental states possible to study scientifically. Steven Pinker says the following: the computational theory of mind resolves the paradox. It says that beliefs and desires are information incarnated as configurations of symbols. The symbols are the physical states of bits of matter, like chips in a computer or neurons in the brain. They symbolize things in the world because they are triggered by those things via our sense organs, and because of what they do once they're triggered. If the bits of matter that constitute a symbol are arranged to bump into the bits of matter constituting another symbol in just the right way, the symbols corresponding to one belief can give rise to new symbols corresponding to another belief logically related to it, which can give rise to symbols corresponding to other beliefs, and so on. Eventually, the bits of matter constituting a symbol bump into bits of matter connected to the muscles, and behavior happens. The computational theory of mind thus allows us to keep beliefs and desires in our explanations of behavior, while planting them squarely in the physical universe. It allows meaning to cause and to be caused. So you see, this is a description of mind as a computational system, as a formal system. So that means that there are tokens, there are rules for transforming those tokens. The rules are the syntax, right? And that means that there's no meaning at the syntactical level. However, the tokens in this interpreted automatic formal system, they are sensitive to meaning in the sense that the rules, even though the rules are not about meaning, the rules are about form, about how the tokens work together. These rules are truth preserving, right? These rules, when applied to tokens, will generate something that makes sense. It will generate something that if you start with true sentences, for example, you're going to end up with true sentences, right? In this case, the sense that the tokens make in combination has to do with the outcomes of the behavior, right? So here's Thagard's general explanatory schema for cognitive science. The target is to explain why people have a particular kind of intelligent behavior, right? That's what we're trying to understand. And the way that we try to understand this is the following. There's a pattern. First, people have mental representations. Second, people have algorithmic processes that operate on those representations. And then the processes applied to the representations produce the behavior. This is a general explanatory schema because it's not specific. It's not specific to any particular intelligent behavior. It's not specific about any particular kinds of representations or kinds of processes, right? But it's just exemplifying, it's illustrating the general approach that we take in cognitive science. That is, we're trying to explain intelligent behavior, and we do that by reference to representations and rules and processes that transform those representations. And when these come together, that's what produces behavior. The words in bold here, they are placeholders. So they can be filled in different ways by different attempts within cognitive science to understand thinking. And that's what we're going to see in the next video, how this general explanatory schema can be made specific, how we can generate specific explanations of intelligent behavior by appealing to some or other theory of what the algorithmic processes are and how these algorithmic processes transform representations so as to yield behavior.